Class 9 Science Chapter 4 Structure of the Atom, and in this video we will discuss about atomic models, Thomson atomic model, Rutherford atomic model and Bohr's model of atom. First come to Thomson model of atom. Thomson proposed that an atom consists of a positively charged sphere and the electrons are embedded in it. What is the meaning of this? Embedded, fixed firmly and deeply. You can see this picture represents the Thomson model. This is a positively charged sphere and these electrons are embedded in it. The negative and positive charges are equal in magnitude, so the atom as a whole is electrically neutral. Important features. Thomson's model explained that atoms are electrically neutral and mass of the atom is assumed to be uniformly distributed over the atom. Drawbacks. The results of experiments carried out by the other scientists could not be explained by this model. And many different names are given to this model. For example, this is also known as plum pudding model. This is a pudding means sweet dish, raisin pudding or watermelon. If we compare with this watermelon, the red part of the watermelon is positive sphere and seeds of the watermelons can be resembled with electrons. Okay. Rutherford's alpha particle scattering experiment. Rutherford and his students Hans Geiger and Ernst Marsden bombarded very thin gold foil with alpha particles. Now what is these alpha particles? Alpha particles are doubly charged helium ions and this is represented like this. The thin gold foil had a circular fluorescent zinc sulfide screen around it. Whenever alpha particles struck the screen, a tiny flash of light was produced at that point. You can see the setup of this experiment. This is the source of alpha particles. This is a beam of alpha particle passing through this hole in the lead plate, strike to this gold foil, and this is a circular fluorescent zinc sulfide screen. Okay. A gold foil was selected because gold is the most malleable metal and he wanted as thin a layer as possible. Observations of Rutherford's alpha particle scattering experiment. Most of the alpha particles pass through the gold foil undeflected. You can see this representation. This represents the thin sheet of gold metal and these represents the gold atoms. And alpha particles are passing from this side, bombarded from this side, and these passed, most of these alpha particles passed straight without any deflection. A small fraction of the alpha particles was deflected by small angles. You can see this one. This is deflected by small angle. Okay. This one again, this is a deflection by small angle. This is also deflection. A very few alpha particles, that is about 1 in 20,000, bounced back, that is were deflected by nearly 180 degree. You can see this alpha particle is bombarded in this direction, again bounced back by 180 degree. Conclusion from Rutherford's alpha particle scattering experiment. Most of the space in the atom is empty. The positive charge is concentrated in a very small volume called nucleus. Now assume if Thomson model is correct, then all the particles should bounce back. Okay. The volume occupied by the nucleus is negligibly small as compared to the total volume of the atom. The radius of the atom is about 10 raised to the power minus 10 meter, while that of nucleus is 10 raised to the power minus 15 meter. Rutherford's nuclear model of atom. The positive charge and most of the mass of atom is densely concentrated in extremely small region called nucleus. You can see this nucleus was discovered by Rutherford. The electrons revolve around the nucleus in circular paths called orbits. Electrons and the nucleus are held together by electrostatic forces of attraction. Rutherford's model of atom resembles the solar system. You are familiar with the solar system, in which the nucleus plays the role of sun and the electrons that of revolving planets. This is also known as planetary model of the atom. Drawbacks of Rutherford model. Rutherford model cannot explain the stability of an atom if the motion of an electron is described on the basis of classical mechanics and electromagnetic theory. Now, what are these two? Classical mechanics is a theoretical science based on Newton's law of motion. You are familiar with these laws. It specifies the laws of motion of macroscopic. Macroscopic means which can be seen by naked eyes. And these classical mechanics or Newton's law can also explain the motion of planets. Okay. When a body is moving in an orbit, it undergoes acceleration. This is the common experience. To maintain the speed, that body has to be accelerated every time. And according to the electromagnetic theory of Maxwell, charged particles, when accelerated, should emit electromagnetic radiation. This electromagnetic radiation is a form of energy. It means when electrons accelerated in a circular path, they emit the energy. And when energy is emitted, the path will shrink like this. Okay, spiraling. This path will shrink continuously, and ultimately that electron will merge into the nucleus. It means atom is not stable, but in practice atoms are stable. It says nothing about distribution of electrons around the nucleus and the energies of these electrons. It only says that electrons revolve around the nucleus, but there is the number of orbits are possible. In which orbit electron will revolve, it says nothing about that. Bohr's model of atom. Only certain special orbits known as discrete orbits of electrons are allowed inside the atom. And while revolving in discrete orbits, the electrons do not radiate energy. That's why atoms are stable. These orbits or shells are called energy levels. These orbits or shells are represented by the letters like K, L, M, N, or the numbers, that is N is equal to 1, 2, 3, 4. Orbits or shells are represented by this N. If N is equal to 1, it represents K shell. If N is equal to 2, this is L shell. If this is 3, this is M shell. If N is equal to 4, this is N shell, and so on. And this is the nucleus. Okay, and these orbits are concentric around the nucleus. How are electrons distributed in different orbits or shells? And for the distribution of electrons, Bohr and Bury gave some rules. These are known as Bohr-Bury scheme or rules. And according to these rules, the maximum number of electrons present in a shell is given by the formula 2n square, where n is equal to 1, 2, 3. That is number of shell. It means in the K shell, value of n is equal to 1, maximum number of electron 2. In L shell, where value of n is 2, maximum number of electron 8. You can find out 2n square. Put the value of n 2. That is 2 into 2 square. Okay, that is 2 into 4. This is equal to 8. In the same way, in the M shell, where value of n is equal to 3, 18 electrons are there. These are the maximum electrons. When n is equal to 4, 32 maximum electrons are there. Okay, the maximum number of electrons that can be accommodated in the outermost orbit is 8. And these electrons are filled in stepwise manner. Now, what is the meaning of stepwise manner? That is, first electron enters lower energy shell. Okay, that is, first electron enters K shell. After the filling of this K shell, electron will go in L, and after that M. In this is the stepwise manner. Now, this table shows the composition of atoms of the first 18 elements with electron distribution in various cells. Now this electron distribution, that is distribution of electrons in various cells, this is known as electronic configuration. Okay, and in this case, this is name of element, this is the symbol, this is atomic number. Now what is this atomic number? Atomic number is equal to number of protons. Okay, and as we know, in atom is a neutral, that's why number of protons are equal to number of electrons. You can see this one, and this is the distribution in various cells. It is hydrogen, H, one electron is there, and this is present in the K shell. Helium, He, number of electrons are 2, these are present again K shell. Lithium, Li, number of electrons are 3. Now in the first shell only maximum 2 electrons can occupy, that's why third electron will enter next cell, that is L, that is 2, 1. In the same way, beryllium, Be, this is 2, 2. Boron, B, this is 2, 3. Carbon, C, this is 2, 4. Nitrogen, symbol is N, electrons are 7, 2, 5. Oxygen, O, electrons are 8. And these electrons are distributed as 2, 6. Fluorine, F, electrons are 9, this is 2, 7. Neon, Ne, electrons are 10, this is 2, 8. Sodium, this is now again 2, 8, 1. In the second cell, maximum 8 electrons can occupy. That's why next electron will enter M shell. That's why this is 2, 8, 1. And magnesium, this is 2, 8, 2. Aluminium, Al, 2, 8, 3. Silicon, Si, 2, 8, 4. Phosphorus, this is 2, 8, 5. Sulfur, this is 2, 8, 6. Chlorine, Cl, 2, 8, 7. Argon, Ar, this is 2, 8, 8. Okay, dear student, you have to remember name of element along with the symbol, what is atomic number of the elements, okay, and what is the distribution of electrons, like this. That is, distribution of electron means electronic configuration of these elements you have to memorize. Now this is the schematic atomic structure of the first 18 elements. The hydrogen, this is nucleus. 1 electron is there in the first shell. Helium, 2 electrons in the second cell. Okay. Now in the lithium, this is 2, 1. It means in the first cell 2 electrons and in the second cell 1 electron. Beryllium, this is 2, 2. Okay. In boron, this is 2, 3. Carbon, this is 2, 4. 2 electrons in the first cell and 4 electrons in the second cell. In the same way, you can write this is nitrogen, oxygen, fluorine, neon, that is 2, 8. Okay, and in case of sodium, distribution of electron, that is electronic configuration, is 2, 8, 1. That's why in the first cell 2 electrons are there, in the second cell 8 electrons are represented, and in the third cell 1 electron is there. Okay, this is magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. I think you are able to draw the atomic structure of these elements. Okay, thank you.